So what we have in this question, what's given to us is that U, which is the potential energy, equals A by R cube. I'm sorry, A by R squared minus B by R. Right? A and B are positive constants, and R is the distance from the center of the field. Okay, what do we need to find? We need to find the value of R naught or R node corresponding to the equilibrium position of the particle. Okay, let's call this R node. We need to find this value. We also need to find what kind of equilibrium that is, and also the maximum magnitude of the attractive force, or the attraction force. Okay, so let's go one by one. Obviously, when we have an expression like this, where this is we have an expression for potential energy in terms of R, we know that we have to use this formula, right? Or you can say this expression where F is equal to minus du by dr, where F is the magnitude of the not magnitude, F is the conservative force, right? And U is the potential energy, right? So we can directly apply this over here, and the question also says that we need to find R in such way that it's in equilibrium position. Well, we know that for equilibrium position, the net force has to be 0. So all we have to do is find minus du by R, equate it to 0, and find the value of R for that particular expression. Sounds pretty simple, right? So let's do it. So we have U over here. For the sake of simplicity, I'm just going to write U as AR to the power minus 2 minus BR to the power minus 1. It just helps me to differentiate easily and faster. Yep. So du by dr, or no, let's say minus du by dr, is going to be minus of d by dr of this. So let's take this minus outside so that we don't get confused. Now if you have to differentiate the first term, there'll be A minus 2 R into minus 2 minus 1. Correct? Cool. Over here there'll be minus B minus 1 R into minus 1 minus 1. Many times what we do when we differentiate is we try to quickly do all this without really writing all this down. I've at least in my personal experience, I make a lot of mistakes because of the negative and the positive, and also just easier and more clear to write down all your negatives correctly, all the values correctly. So here minus will become minus 2a r to the power minus 3. Minus and minus is cancelled, so you get plus b r to the power minus 2. Correct? And this will then be equal to, if I bring the negative inside, 2a r to the power minus 3. Let me just write this by r cube minus b by r squared. Correct? This is the value of minus du by dr, or force. Now we have to equate this to 0, right? If we equate this to 0, then we get the value of R naught. So at R naught, by R naught cube minus B by R node squared should be equal to 0. Correct? So if I factorize this, 1 by R node squared into 2a by R node minus b equals 0. This implies that obviously R naught squared cannot, 1 by R naught squared cannot be 0, which means that we have only this factor that should be equal to 0. So 2a by R naught minus b should be equal to 0, which implies that b B. This the R node equals to A by B. Okay. So at this particular value, when R equals 2A by B, this is when we have an equilibrium condition. Cool. The first answer we got. The second question is to ask what kind of equilibrium this is. How do we do that? What are the conditions for equilibrium? What are the different types of equilibrium? There's stable equilibrium, there is unstable equilibrium, and I think there's neutral equilibrium, right? But how do you know? Well, what is stable equilibrium? We know that if displaced from that position, the object should come back to that position. Unstable is when you displace from that position, the object should move away from that position. A simple example is when you have a curve like this and the object is at the bottom, you know that's at stable equilibrium because when you push it, it'll come back, right? Similarly, if you have a curve like this and the object is on top, unstable because if I push it, it will move away, it will fall down. So that's in a state of unstable equilibrium. Neutral equilibrium is probably when there's a flat surface. You take a ball and you push it, it's just going to move. It's not, it's not stable or unstable, right? So these are the different types of equilibrium. So how do you figure this out? Well, in the case, I'm pretty sure you know already that in the case of stable equilibrium, the potential energy, right? The potential energy versus R, right? U versus R curve will also look like this. Will curve up like this. In the case of a stable equilibrium, which means that the second differential, the double differentiation of du by dr, the slope should start from negative and then become positive, which means that it should be greater than 0. Correct? So in the case of stable equilibrium, now if I'm just going to draw a sample graph like this, let's say this is potential energy versus R, the graph will look somewhat like this. Okay, it's important not to get confused here. This is not the curvature of the surface. I know that the curvature of the surface will also look like this, but what's beautiful is that the graph between U and R will also look like this in the case of stable equilibrium. Okay, it kind of makes sense, right? Because if you do this, if you push it, the potential energy of the system is increasing. Right? Similarly over here also it's increasing. So similarly over here, at this point, let's say this is that point of stable equilibrium. Now, if you move this body in this, you can see that in the graph is showing that. So this is U, this is R. It's showing that as you change R, U is increasing, which makes sense. Correct? So the graph will also look like this. But what does this tell us? This tells us that this is a minima. It's a point of minima for du by dr. Correct? Or at this point, if I take du by dr, the slope will be 0. This is the slope. The value of du by dr at that point should be 0. That makes sense because that's what we found, right? But how do we know if it's stable or unstable? This will be true only when the slope before this, for example, is negative over here, and the slope after this over here is positive, right? Which means that the double differential, that is d square u by dr squared, should be greater than 0. Only then this works, correct? If it's the other way around, if it's like this, then the double differential will be less than 0, correct? Because this will also be a slope. This will be one of the solutions. This point will also be one of the solutions, but this will be a point of maxima if the double differential is less than 0, correct? This is this basic maxima and minima, so on and so forth. So what we're basically doing is finding the minima of this graph. Okay, so how do we do that? We already know. We've already differentiated du by dr. Correct? Oh no, we found minus du by dr. So let's do one thing. Let's find du by dr. Because f is minus du by dr. So here we have u, which is equal to minus d by r. Right? This is what is given to us. Again, this is equal to a to the minus 2 minus b r to the power minus 1. Now we found minus du by dr, so let's just directly differentiate du by dr. That will be cool. So we have du by dr equals this expression. Let me just simplify this. This becomes minus 2a into r to the power minus 3 plus b into r to the power minus 2, right? Now what we have to do? So this is du by dr, but what we need to find is the double differential, right? We need to find d square u by dr squared to check if it is stable or unstable at that point. So we directly double differentiate. Okay, so let me quickly do this. So this becomes minus 2a minus 3 r to the power minus 3 minus 1 plus minus 2b plus r to the power minus 2 minus 1. Right? Minus 3 minus 1 basically is minus 4. Minus 2 minus 1 is minus 3. It makes sense. So now if I just expand this, so this becomes plus 6a plus 6a by r power 4. Okay. Then minus 2b by r cube. Yep, that looks fine. Now, what do we do? Now, for this value of d square u by dr squared, we need to substitute the value of our node that we initially found, because we need to check if that value is positive or negative. So if I substitute that, if I say this at our node, which is equal to, we got r node equal to 2a by b. So I'm going to substitute this value in this value of this thing we got. So we have that will be equal to 6a by 2a to the power 4 into b to the power 4 minus into b cube. We have to find if this value is positive or negative. How do we do that? Let's see if we can simplify this. Okay. So this will become 6a into b to the power 4 by 2 power 4, which is 16 into a to the power 4 minus 2 into b to the power 4 raised to the power 4, 8 into a cube. Okay, this is what we're getting. Quickly just factorize all this. It becomes 1/4. B to raised to the power 4 divided by a cube. Minus 1/4 into b raised to the power 4 divided by a cube. Now what do we do? Nothing, we just take this, we factorize this again. So this becomes 4 by 8 cubed. 3 by 8 minus 1 by 4. 3 by 8 minus 1 by 4. Okay. Reduce further. So 8 3 minus 2, which will make it 1 by 8. So finally you get 1 by 8 into e to the power 4 raised by 8 cube. So yeah, so finally this is the value that we get, and what do we know about this? This is obviously greater than 0 because b and a has been given to us. They are positive constants that's multiplied into a positive number. So obviously this is positive, right? And this tells us that at this point the equilibrium will be stable equilibrium. Cool. Now let's come to the last part of the question. It says, find the maximum magnitude of the attraction force. There's maximum magnitude of the attraction force. How do we do that? Well, what do we know? We know that for the force to be attractive, it has to be negative. Right? Only if the F is negative, only then it's an attractive force. If F is positive, it's a repulsive force. Correct? So which means that if I had to draw, let's say, a random graph, sample graph like this, if the force was somewhere over here and this was the point, then that would be a positive force. This area will be a positive force because I have, in this case, I have F over here and R over here. But if the graph was somewhere over here, let's say, and this point, the force will be negative, right? Which means that at this point it will be attractive. But what we need to find is the maximum value of the attractive force, which means that the graph should look like this, something like this. At this point, the attractive force, first of all, the force is attractive, and the magnitude of the force is also maximum because it's the maximum negative value. So at this point, whatever that point might be, let's call it R1 or something. At that point is where the force will be maximum and it will be attractive. So we basically have to find this point. So if you look at the graph, what we have to do is find the minima. We have to find a minima which is also negative. Correct? Cool. So let's do that. How do we do that? Well, first we know, of course, this is R. What is given to us is U, but using U we can find F, and we've already done that before. So we found that F is equal to minus du by dr, and that is equal to 2a by r cubed. Correct? We found it somewhere. F is equal to 2a by r cubed minus b by r squared. So minus this is something we already found out. Now what we do is we find df by dr, correct? Because that will give us that way we can figure out which are the points where the slope is 0, right? So df by dr is equal to basically differentiation of this, which will be, so I'm going to write r to the power minus 3 and r to the power minus 2. So this will become 2a into minus 3, r to the power minus 3 minus 1, which is minus 4, minus of minus 2 into b r to the power minus 2 minus 1, which is minus 3. Right? So this will become minus 6a by r to the power 4 plus 2b by r cubed. This is the value of df by dr. Okay. Now what do we do? Now we have to find obviously the point where this point, to find the minima, we need to find the value where this is equal to 0. Correct? So let's equate it to 0. This doesn't prove that it's a minimum, it just finds a point where the slope is equal to 0, right? So if I equate this to 0, I'll find minus 6a by r naught 4 plus 2b by r naught cube equals 0. This, find the value of r naught. It's because the same thing, it's the same calculation. I'm going to do that again, and I'll get r is equal to 3a by b. This is again something that we've already done. You basically find the point where the force is 0, right? No, but this is not enough. We just know that the slope is 0. We still don't know if it is a maxima or a minimum. So for that we have to double differentiate. So we have to find df squared by d square f by dr squared, how you want to call it. So if we double differentiate this value 6 equal to this will be this value, which will be minus 6 into minus 4 minus 5, correct? Minus 4 minus 1 and plus 2 into minus 3 r to the power minus 3 minus 1, which is minus 4. Okay, so this is just basic algebra, so I'm just going to directly go to the last step over here. So what do we get finally? A square. You get 6 by r per. Does this look right? Yeah, this is fine. R by 5, this comes out perfect. So you get 6 by r. This is the value that you get. Okay, this is the value of d square f by d square. Now we have to substitute this value, which is r node. Right? R node equals to 3a by b. We have to substitute that in this and check if we are getting. First of all, find out. We also have to find we have to substitute this and find the value of f. Before we do that, to check if it's positive or negative, first we also need to find the maximum value. We need to check and see if the value of f itself is negative or not, right? So for that, you substitute r node at this value in the equation of force. So basically, f at r node magnitude will be equal to 2a by r node cube minus b by r node squared, which is equal to 2a by 3a whole squared, cube minus b by 3a squared into b squared. Simplify this, I get 2ab cube by 27 a cube minus b cube by 9 a squared. Correct. And this, if I simplify further, I get basically minus b cube by 27a squared. This is the final value we get, and we can see obviously that this value is negative. That's what we needed to find. So this tells us that the force at that point is negative, which means that it is an attractive force. So that's good. Okay, now we have to check if it is. We still don't know if that doesn't give us the final answer. Now we have to find if it is a maxima or a minima at that point. For that, we have to substitute basically our R node in this and check if it is positive or negative. I know this feels a little complicated, but it's not. It's just that. So first, basically what we're doing is we're finding f, then we find df by dr, and we're finding the value of R node. For that R node, we are substituting in the value of f to figure out if that f is positive or negative, and we got that it's negative. This tells us that it's an attractive force. Now we are finding d square f by, or double differential, finding this expression. Now again substituting R node to check if it is a maxima or a minima. So let's quickly do that. Six by R node power 4, so d squared L squared at R equal to R node will basically be this is our final expression. Okay, so in this, obviously we have to check if this is positive or negative. We have two terms. So over here, 6, it doesn't really matter if, 6 by R node power 4 is obviously positive because R node is 3a by b, and we know that's a positive number. So 6 by positive number will always be positive. So this number will, we just now therefore have to check if this expression 4a by R node minus b, if that is positive or negative. So just quickly, I'll just substitute that and I'll check. So 4a by R node is what? 3a by b minus b. Right? This thing gets cancelled, so we finally get 4 by 3b or minus b, which is equal to 1 by 3b. Correct? Yeah, and this we get is a positive number because b is also a positive number. So it tells us that the double differential at that point is positive, which means that this is a local minima. So therefore, the graph does look like this. Like this, right? It's at this point. Therefore, the magnitude of that force we've already found is this value, except that this is negative, so the magnitude of that force will be b cubed by 27a squared. So that is your final answer. Right? So we've proven that it's negative, we've proven that it's a minima, and we've also found the magnitude of the force. So here we have another interesting problem. So what does it say? It says that a small bar A, let's call this A, is resting on a smooth horizontal plane, is attached by a thread to the point P. This is meant to be point P. And by means of a weightless pulley to a weight B possessing the same mass. So let's call this B, this is B. And the masses are the same. So let's say this is M and this is also M. Besides, the bar is also attached to a point O by means of a light non-uniform spring of length LO. Basically, they're saying this length is LO. And more importantly, this is the natural length of the spring. X, which is the stiffness, is given to be 5 mg per LO, where M is the mass of the bar. Oh, okay. But I just like to call it K, so let's call it K because in my calculations we generally use K for it. So let's say K is equal to 5 mg by LO, right? Where M is the mass of the bar and LO obviously is the length. thread PA having been burned, the bar starts moving, find its velocity at the moment when it is breaking off the plane. So they're saying that this thread is going to get burnt. If you remove this, what's going to happen? Obviously, the weight B, mass B is going to move down, and therefore is going to pull A in this direction, right? Now, at some point, A is going to come off this ground, right? And they're asking, find its velocity at the moment when it's breaking off the plane. We need to find the velocity V. Let's call it V. Velocity of A, basically, at which the point at which it will come off. Obviously, the velocity of B will also be the same because they're constrained, they're moving along the same string, but still, velocity of A at the point where A will come off the ground, breaking off the plane. Okay, how will you do this? So let's draw the end condition. Okay, I've already pre-made diagram over here. As you can see here, B has moved down a little, A has come over here. This is B, this is A. After the string has been burned off. Now let's assume this is the point where A is just going to come off the plane. Okay. Now, what is going to happen? Let's try to draw the forces over here. Okay. So we know that this distance, the spring, the force on the spring is going to be in this direction, and let's call that Kx, where x is the delta. X is the difference from the natural length of the spring. Okay. There is of course going to be tension in this direction. Use the same color. There's tension in this direction. There is no friction, so that's fine. And there is gravity in this direction. Now you may think there's normal force also, but at the point when it's just about to break off, normal force will be zero. Right? We can assume that there is going to be no contact. So for all practical purposes, there is no normal force. So these are the only forces that are acting here. Now, to make things simple, I'm going to, so this is okay. No, actually, let's leave this as Kx. Okay. Now, I'm going to draw the let's assume that to get the angle theta, let's assume that this distance, if I drew a line like this, then this distance or this angle, let's assume is theta. Then if I resolve Kx, I'll get one force in this direction, Kx sine theta, right? And the other force in this direction, Kx cos theta. Okay. So here I have Kx cos theta, correct? So if I look at just the vertical direction, then at that point, Kx sine theta should be equal to mg, right? Because there is no normal force. Or in other words, I can say that x, which is the extension in the string, should be equal to mg by k sine theta. Now we also have a value for k. K is given to us, so I'm going to substitute that. K is equal to 5 mg by LO, which means that mg by 5 mg, this will come into LO over here, into sine theta, right? So mg will get cancelled. So finally, I'll get LO by 5 sine theta. Okay. Now, what is sine theta exactly equal to? Because sine theta is, again, we don't know, right? So we have to write it in terms of values that we already know. Now, if you look at this triangle, to make them simple, I'm going to call this, what's this given to be? Let's say O. This is O, this point is O, this point is, I don't know, P is already given to us. Let's call this R and this S, this point S. If a triangle, look at the triangle ORS. OR is the opposite side of the angle and RS is the base of the triangle, correct? which means that sine theta should be equal to OR by RS, or OR we know is the length of OR is already something, which is LO, it's given to us, and RS, let us give some value for it, let's call it D, right? So this distance from here to here, the distance that the block moved horizontally, I'm going to call D. Okay, so that means sine theta, I'll write over here, sine theta equals, not LO by D, it will be opposite by hypotenuse, so LO by the total distance, so that will be LO plus X, right? The hypotenuse over here is OS. OS is the hypotenuse, and that is the total length, which is LO plus the extension in the spring, which is X. So sine theta equals LO plus X. Cool. So that I'm going to substitute over here. So this value of sine theta I'm going to substitute over here. So if I do that, I'll get X is equal to LO by 5 into sine theta, which is nothing but LO by LO plus X. So there will be LO here into LO plus X, right? So this LO and LO will get cancelled. So finally we get LO plus X by 5. Okay, so if we simplify this further, so I get 5X equals LO plus X, right? Which means 5x minus 4x equals LO, or X equals LO by 4. This is important. So we finally found that at that point the extension will be equal to LO by 4. Okay. Now what do? Now the question says we need to find the speed of the block when it's going to come off. Now generally most of the times when there are questions involving speed, finding the speed of a block, most likely it will involve conservation of energy, right? Because that's where we have terms with half mv squared, so on and so forth. So let's conserve energy. So initially in this state, when the block was in this position, nothing was moving, right? The initial energy is 0, right? Because the spring is in its natural length, both the objects are stationary, nothing is moving, everything is, at 0 energy. Of course, we can assume that the height, there is some height for the block B, but let's assume at that point it's at 0 potential energy. Right? We can keep our reference wave anywhere. Let's assume at that height, when the block is at B, at that point, when the initial position, the potential energy is 0. So the overall energy is 0. Now, when we come to this case, when it is extended like this, I know there are a lot of things happening, but what is the total energy of this system when it's moved over here? Let me write it over here so that it becomes a little easy. No, actually no, too complicated. So I'll write it over here. The energy of the system will be the spring will have potential energy because it's extended, and we know that the potential of the spring will be equal to half kx squared, correct, where x is the extension, k is obviously the spring constant that's given to us. What else? What is the other end? The blocks will have kinetic energy because they'll be moving with some speed v, and that's what we need to find. So and both of them will move with the same speed because they're constrained by the string, right? They're connected to the same string. So it will be 2 into half mv squared, basically per block, right? What else? Is there any other energy? You might think that that's the end, there is no other energy, but there is one more. There is actually loss of energy, or you can say that the potential energy has reduced because the block B has gone down, right? So the change in potential energy will be negative, and it will be minus mg by some distance. But that distance we know. So because we are assuming that block A has moved this distance through a distance d in this direction, then the block B should also move down. Let me draw this over here. If this was the initial position, like this, right? This displacement that this block would have had from here to here will also be d, correct? Because we're assuming block A moved through a distance d, then block B also would have moved through a distance d, right? So the change in potential energy will be minus mg into d, correct? So this is the overall energy of the system. Okay, it's important to understand here it's only minus mgd for this because I'm assuming that at this position, when the block was at this position, the potential energy was 0. That's why now it's become negative. Okay. So this is your final energy. So this means because the initial energy is 0, we can just directly say that 0 should be equal to this because by the law of conservation of energy is conserved. Like there can be the initial energy should be equal to the final energy, right? So then I can just write, if I expand this, we know K is equal to what? K is given to be, let me just check, 5 mg by LO. So I'm going to expand this half into K, which is 5 mg by LO into x squared. But x we already know is LO by 4 the whole squared, correct? Plus 2 and 2 will cancel, so this will be m into v squared minus mg into d. Okay, let me just simplify this first before I do anything else. So, this is equal to 0. Okay, this means that phi by 2 mg by LO into LO squared by 4 squared, which is 16. So this get cancelled, plus mv squared minus mgd equals 0. How do we simplify this? Oh, looks like we can't simplify this. Cool. So this will be phi by 16 into 32 into mg LO plus mv squared minus mgd equals 0. Of course, I can remove m because m is common here and m cannot be 0. So I can directly remove m. So we get 5 by 32 LO minus gd equals 0. Now we have an equation, but the problem is we have two unknown. Like we have of course we have to find v, that's the answer that we need, but we have it in terms of d, and d is a value that we don't know, so we have to convert it into values that we already know. For that, we'll go back to our diagram over here. In this diagram, thanks to that nice right angle triangle ORS, the value d, right, should be equal to OS squared, basically the hypotenuse, minus OR squared or LO squared, OR squared square root of that, right? Because just simple by Pythagoras theorem, we know that the sum of the squares, square of the base plus square of the height should be equal to square of hypotenuse. So this can be written as OS squared is what? OS we know is LO plus X. So LO plus X the whole squared minus, I think this is getting a little crowded, so I'll just write it down a little over here. So OS squared will be LO plus X the whole squared minus OR squared. What is OR? OR is LO itself, right? LO squared root of this. This will give you D, correct? So let me expand this and simplify this over here. equal to minus LO squared. That's what we got. If I simplify this, what do we got? LO squared minus LO squared will get cancelled, so it will be x squared plus 2LOX. Yeah, LO squared minus LO squared. So this is your value. This is the value of D that we get. X is LO by 4. Correct? Yeah, X is LO by 4. So that I substitute over here again. LO by 4 whole squared plus 2 into LO by 4. Right? So this will be LO squared by 16 plus 2. So this will be LO squared by 2. Right? Yeah. This will be equal to LO squared into 1 by 16 plus 1 by 2 which will be 1 plus 8, right? LO squared into 9 by 16 root over this. Now the root of this is nothing but LO into root 9, which is 3, into root 16, which is 4. So finally we get 3 by 4 LO, right? We get a nice number. So this is the value of D. That's what I've done, right? I got the value of D. So now, as I said, we're going to substitute this value of D that we get 3 by 4 LO in our initial equation over here to find the value of V. So if I do that, I'll get 5 by 32 LO into G plus V squared minus G into D, which is 3 by 4 LO. 3 by 4 LO equals 0. So this implies that V squared equals 3 by 4 LO into G minus 5 by 32 LO into G. Okay, now I'm going to take LO into G out common and I get 3 by 4 minus 5 by 32. Okay, this will be what? LO G. 32 will be the LCM. 24 minus 5 is equal to LO into G. 24 minus 5 will be 19 by 32. Okay, now I can substitute the values. Let's say the question doesn't say what. Let's assume G equals 10 meters per second squared for the sake of simplicity. Okay, so if I substitute G equals 10 meters per second squared and LO equals to what's given to us? LO is given to be 50 centimeters, which is 0.5 meters. Right? If I substitute that in this value, I get V squared equals 0.5 or 1 by 2 into 10 into 19 by 32. And V will be the root of this. Now you can calculate this. Now this is just simple calculation. You'll find that this value will come approximately equal to, V will be approximately equal to 1.7. .7 meters per second. So that is our answer. So at that point, just before breaking off, it'll have a speed of 1.7 meters per second. So I hope you enjoyed solving these problems. And if you want to solve more like these, please subscribe to the channel.
For more videos and live lectures on the JEE, click on the subscribe button now.